Good morning. Let us start our today's lesson. I am going to consider one more example, namely, suppose that we consider a diffusion process for which A as x is equal to identity with 0 and B as x does not depend on S and X and is a given matrix B. For operators, or we will consider a fixed orthonormal basis. So this is a matrix, and this matrix is non-negative definite, but let us suppose that it is invertible. So there exists the inverse matrix operator b minus 1, b to the power minus 1. Okay, so the Kolmogorov backward equation looks like the following one: du ds plus 1/2 the sum over ij from 1 to v, b ij e to u dxi dxj equals 0. If B is an identity matrix, then this is nothing else but the heat equation. Okay, and we solve which function is the fundamental solution to the heat equation. Okay, in this case, how to write down the fundamental solution? Let us denote by Bij the entries of the inverse matrix. Okay, and this is an easy exercise to show that the fundamental solution to this equation is the following function: 2 pi t minus s to the power g determinant of b to the power minus 1 half minus 1/2 and exponent minus b minus 1 y minus x y minus x over 2 t minus s. It is an easy exercise. You should calculate these derivatives with respect to of this function with respect to x. And
recording in progress.
And the those calculations show that this for fixed ty, this function is a function of Sx in the region Sx. In this region satisfies this equation. And it is not difficult to verify that G S X T Y can be estimated by some constant t minus s to the power minus d over 2 x minus mu the norm of y minus x to the power 2 over t minus s for all s x t y such that s is less than t. Moreover, g dx j of s x t y absolute value for all j from 1 to b can be estimated by the following expression: t minus s to the power minus d plus 1 over 2 x minus mu y minus x square over t minus s, where k is a positive constant. It depends on mu. Mu is also positive, and it is not difficult to see that mu that b minus 1 y minus x y minus x scalar product. This is a non-negative number. Moreover, because our matrix is invertible, so this is some constant C1, where C1 is positive. We can choose C1 being equal to 1 over the maximal
if theta is y minus x.
Theta. I'm sorry. yes, y minus x squared. And C1 can be chosen being equal to 1 over lambda max. Lambda max is a maximal eigenvalue of this matrix B. Okay, and now mu, we saw how this mu can be chosen. Mu must be less than this number for this derivative. Here we can put mu being equal C1, but here mu must be less than that number, and I can write down here the number that is less than this one. Okay? And what is very important for us, that the second derivative dxj dxk in absolute value can be estimated by the same constant t minus s minus d plus 2 over 2 x minus mu y minus x squared over t minus s. Okay, this is an exercise. These derivatives can be easily calculated, and we saw in the case where b ij equals delta ij, Kroneker's symbol, we saw that these estimations are valid, and in this case the same estimation. We have the same estimations. Okay, and now we start the material that is called parametrics method for constructing the fundamental solution to the Kolmogorov backward equation in the general case. So let some functions a s x and b s x on the set s x belongs to 0 t or b be given such that the following assumptions are fulfilled. There exists some constants C1 and C2 such that C1 norm theta square is less than B S X theta theta, and it is not greater than C2 norm theta square for all theta from RD S X. Let us denote this region by dt.
So is it possible that C1 is 0 or C1 must be positive?
Oh, no. Strictly positive. Thank you. Yes. And we need that DSX is non-degenerated. Okay. The second one. There exists some constant K and alpha such that B I J S X minus B I J of T Y absolute value is less than this constant K times T minus S to the power alpha over 2 plus the norm of x minus y to the power alpha. For all s x dt and ty from dt, and all ij from 1 to t. In other words, the functions bij must be Hölder continuous. And the third condition, the function ij of Sx the functions for all j from 1 to d, they are continuous in both arguments in this region and bounded and they satisfy the Hoover condition with respect to space variable. Same constant k and to the power alpha plus x and j equals 1. Okay, under these conditions, we will construct the fundamental solution to the Kolmogorov backward equation with coefficients Bij, Ij, Aj. We start from the following function. G0 S X T Y being equal to 2 pi t minus s to the power g determinant b we first investigate some properties of this function. It is not as a function of y, it is not a density of some distribution, probability distribution, because you see y is here, okay? But it satisfies the following as a function of Sx. It satisfies the following equation: dg0 s x ty ds plus 1/2 b t y (1/2). Let us write down in coordinate form the sum over Oj from 1 to d b Bij of ty y I minus xi yj minus xj I'm sorry. Not Bij ty d2 g0 dxi dxj s equals 0. This is exactly that example that we have just considered. Okay, bt y, this is some constant. If we consider our function as a function of sx, so bty is a constant. So we have this equation for this function as a function of sx. Okay? Now, now we observe the following, that this function has the following properties. Because the matrix Bij is non-degenerated and bounded, and its entries are bounded functions, we have the same estimation for gsxt y. It is, this function is non-negative, okay? It is positive. So there exists some constant k, and t minus s must be written here to the power minus d over 2 x, some constant norm y minus x squared over t minus s. Okay? Because here we have inverse matrix, and it is strictly positive definite. So some constant nu exists, and derivatives dg0 sx ty dxj can be estimated by the same constant t minus s to the power d plus 1 over 2 . And the second derivative, d2 g0 sx ty dx I dxj can be estimated the same constant t and mu, but t minus s is to the power d plus 2 over 2 mu y minus x squared over t minus s. The same holds true for the derivative with respect to s. dds is equal some the sum of the second derivative of this kind. So okay, this is the first observation. We see that G0 has can be estimated. G0 and its derivatives can be estimated like the fundamental solution to heat equation. Okay, and now we need one more property of this function, G0. Let us consider some function f of s, x, are from our region dt. Suppose that it is continuous and bounded, and consider the following integral over Rd f of tau z G0 s x tau z dz. We calculate the limit of this integral as tau goes to s. So let us change the variable in this integral according to the following rule: z minus x over square root tau minus s equals y. Not y. Equals z tilde. So we have that this is equal to integral over Rd f of tau z is equal x plus z tilde square root of tau minus s. And here we have two pi determinant b t x plus z tilde square root of tau minus s to pi to the power g, and this all to the power 1/2 minus 1/2, and exponent times exponent minus 1 over 2 b of tau. I'm sorry, here must be tau, not t, yes? Tau. B tau x plus z tilde square root of tau minus s to the power minus 1 z tilde dz tilde. Okay? And now you see b is a continuous function in all its arguments, so this goes to b as tau goes to s, b s x. Okay? Determinant is a continuous function of, so here we will have, we will have in the limit x v s x z tilde, and there is an integrable Maserand, yes, because b minus 1, excuse me, b minus 1. Okay, so we can pass to the limit in this integral, and we see that it converges as tau goes to s, it converges to f s x. We will use this property.
And do we assume that f is bounded and continuous?
Yes. F s x is bounded and continuous in both arguments, in all its arguments. Okay. Estimation, equation. So now,
Sorry,
yeah,
can I ask something?
yes,
Should be the division by square root of tau minus s as we change the variable of integration?
dz equals
Yes.
tau minus s to the power minus d over 2 dz or plus dz tilde. Okay? This is my change of the variable, and dz,
Yes.
okay? Okay, and now let us make one more observation about this function. Let us denote by L the operator in Kolmogorov's backward equation, du ds plus the sum over all j I j s x du dxj plus 1/2 the sum over all ij from 1 to d b ij of s x d2u dxi dxj. And now fix some t and y and consider s x from the following domain. Okay? We fix t and y and consider this function as a function of two arguments, c and x, s and x. Okay, so if I apply this operator to this function, g0 ty of sx is equal the g0 ds argument plus the sum over all j from 1 to d ij sx du dxj plus 1/2 the sum over all I and j from 1 to d dij of sx dg0 d2 g0 dxi dxj. And I know that as a function of sx, g0 satisfies this equation. So I can subtract this equality from this expression because it is 0. So I can write down that it is equal to the sum over Oj from 1 to d ij sx d. I am sorry. Of course, here must be g0. Okay. AJSX dg0 dxj plus 1/2 the sum over all j and I from 1 to d bij of sx minus bij of ty, okay, d2 g0 dxi dxj. You see, we saw in our previous lesson that the second derivative, the estimation for the second derivative of this function is not so good in some sense, but we have here from this function some very nice multiplicator, because according to our assumption, this difference can be estimated by s minus t to the power alpha over 2 plus y minus x to the power alpha with some constant. Okay, and this circumstance makes our estimation not so good, not so bad.
Sorry.
Yeah. So let us make a little break. See you later. So denote this expression by
Recording in progress.
R S X T Y. This is some kernel, okay, and it can be estimated as follows. You see this second derivative estimated by the constant t minus s to the power minus d plus 2 over 2 x minus mu y minus x to the power square t minus s. Okay, so if I consider this this factor times this one, I obtain here plus alpha 2. Okay? And some constant here. Okay, and this multiplicator, this factor, maybe it would be better if I write down it here, times y minus x to the power alpha.
You have to add the. You multiply by both.
Yes, one of them. Okay. If I multiply this derivative on this factor, so I can write down this as t minus s to the power minus d plus 2 over 2 plus alpha over 2 x minus mu y minus x squared over t minus s y minus x over square root t minus s to the power alpha. Okay? And this exponent times this factor can be estimated by a constant exp mu prime y minus x squared over t minus s, where mu prime is less than mu. Okay, and this constant depends, of course, on mu and mu prime. So you see, we have in both cases, we have this estimate for any item in this sum. We have some constant mu. Maybe this mu is not the same as here but some mu, there exists some positive mu and constant k such that we have here this estimation. So every item in this sum. Okay, and now we have one more term here. How about this? We know that dg0 dxj is estimated some constant t minus s to the power minus d plus 1 over 2 x minus mu y minus x square over t minus s and I can write down here d minus plus, okay, d, I can write down 2 minus 1/2
plus 1/2
plus 1/2, and 1/2 is greater than alpha over 2. because not less than alpha over 2, because we supposed that alpha is from the interval 0, 1. So I can write down here alpha and times t minus s to the power 1/2 minus alpha over 2. This is non-negative number, okay? This number is non-negative, and this factor is not greater than t to the power 1/2 minus alpha over 2. So we have the following estimation. Our kernel R S X T Y, that is defined by this equality. This is nothing else but this expression. Absolute value can be estimated by k t minus s to the power minus d plus 2 over 2 plus alpha over 2 x minus mu y minus x squared over t minus s. Okay, and this estimation is nice because if we integrate this estimate, this function, dy over rd, it is some constant c, t minus s to the power d over 2. So after this integration, we will have here k t minus s to the power minus 1 plus alpha over 2 after integration. And if and this singularity at the point t equals s is integrable. That's is very important. Now we are going to seek the fundamental solution in the following form. I denote it by GSXTY. This is the fundamental solution to the Kolmogorov backwards equation corresponding to these coefficients. Okay, and I'm going to seek it in the following form. that function g0 s x t y plus some correction. Integral from s to t d tau integral over rd g0 s x tau z, and here some unknown function tau z t y dz. Okay, and what does it mean that g, the function g, is a fundamental solution? It means that that function must be continuous in all its arguments, and as a function of Sx, it must satisfy for fixed t and y, satisfy this equation. Okay, so if I apply to both sides of this equality operator L, I will obtain 0 is equal L G0. This is our kernel R S X T Y. And now I have to apply operator L to this integral. You see, we have S in two places here. If I take derivative with respect to S, so I must write down here the integrand for this integral, integrand at the point tau equals S. But we saw that if tau goes to S, then this integral goes to Q S X T Y with the sign minus, because here is the lower bound, minus Q S X T Y. And if I write down that operator L under the sign of the integral, so I obtain the integral kernel R S X tau Z Q tau Z T Y dz. You see, we have obtained the integral equation for this unknown function Q. That integral equation can be rewritten as follows: Q S X T Y equals R S X T Y plus integral over s from over the interval from s to t d tau integral over rg r s x tau z q tau z t y dz. And what is very important for us is the fact that this cabinet, this integral equation, has a weak singularity, integrable. This singularity is integrable at the point S. So we can apply the method of consecutive approximations for solving this equation. How it can be solved, this equation. We should put Q0 S X T Y being equal to R S X T Y, and for K greater than or equal to 1, we put QK SX TY is equal to integral over the integral over the interval st d tau integral over rd r s x tau z q tau z ty dz. If we obtain not bad estimation for
Dr.
qk,
Ivановich, there is no k in the right hand side.
yes, and thank you, qk minus 1.
And are you going to add r to the right hand side?
No, no, my solution will be the sum over all k from 0 to infinity, qk sx ty. If I obtain some not bad estimations, then this must be a solution to this integral equation, this sum, this series. And how to estimate them? Maybe let us formulate some proposition. Proposition. Suppose that we have two functions h I of S X T Y I equals 1, 2, and S is less than T, T X from RD and Y is from RD. Okay, and let each function H I S X T Y can be estimated as some constant C I T minus S to the power minus beta I X minus mu y minus x square over T minus S. Y equals 1, 2. Mu is the same. Okay? And Ci and beta I must be maybe different. And suppose that beta I is less than d plus 2 over 2. Then the function hs x t y being equal to integral over rd h1 s x tau z h2 tau z ty dz. Then h can be estimated as follows. Absolute value of hs x t y is less than C1, C2, square root, maybe pi over mu to the power d over 2 t minus s to the power beta 1 plus beta 2 minus d plus 2 over 2 times exponent minus mu y minus x squared over t minus s.
So the power is negative beta I. So if beta is larger, then singularity is worse.
Beta?
No, but there, if beta is larger, then singularity is better.
No, this, each one is less than d plus, each one is less than.
Yeah, I see, but my question is, so hi has a singularity.
Yes.
at 0. And if beta I increases, then singularity become worse and worse.
Yes.
Yes, but singularity of convolution becomes better and better.
Yes, yes, and
Okay.
this is very, very nice fact for us. You see, we are going to solve this equation by iteration, and each iteration will be better than the previous one. Okay? How to prove this proposition? You see, if you have the integral mu y minus z square over t minus tau e to the power minus mu z minus x square over tau minus s dz. This is the convolution of two Gaussian functions, and it can be easily calculated, this integral, and it is equal p over mu to the power g over 2 t minus tau to the power g over 2 tau minus s to the power g over 2 t minus s to the power g over 2 and exp minus mu y minus x square over t minus s. So this inner integral can be calculated. The estimation. We have here the product of two exponents like this. Okay? And it is calculated, and you see this factor does not depend on tau, so we should integrate this function, and here we will have tau minus s to the power minus beta 1 and t minus tau to the power minus beta 2, and these and you can easily calculate this integral, and we see, oh, I forgot to write down here the main factor. You receive here, you obtain here exactly this t minus s, and I am sorry, that integral from s to t gives the Euler's beta function beta over beta of d plus 2 over 2 minus beta 1 d plus 2 over 2 minus beta 2. It's very important because this factor allow us to conclude that the series for Q is convergent. Okay, so we can use this proposition to estimate Qk by induction on K. And those estimates are as follows. Qk of Sx Ty absolute value is so now this constant is fixed. We fix.
Nikolaievich, may I ask one more question?
Yes.
Is it true that constant beta 1 plus beta 2 or minus beta 1 minus beta 2 plus d plus 2 over 2?
No.
So beta 1 plus beta 2 minus this?
Yes.
So it is. So this value is negative,
Maybe.
but maybe positive too.
Maybe positive. From starting from some k, we will have here t minus s to the power to the positive power. Starting from some k. Okay. So qk is so this we fix this k and this nu are fixed, and this alpha is a number in our assumptions. That number is from the interval 0, 1. Okay, and k to the power k plus 1 p over mu pi over mu to the power k d over 2 gamma of alpha over 2 to the power k plus 1 over gamma k plus 1 over alpha over times alpha over 2 and t minus s to the power k plus 1 over alpha times alpha over 2 minus d plus 2 over 2 and exponent mu y minus x squared over t minus s K equals 0, 1, and so on. K, I would like to draw your attention to the fact that K depends on this T. Okay? Not only. It depends on mu, K and mu. Are some constants. Okay. So, you see, the series of consisting of Q, K, S, X, T, Y is convergent. Okay? And this is a solution to this integral equation. And it is not difficult to see that there is a unique solution to this equation, because if we subtract two different equations, so for the difference we will have the same equation without this term. So this term.
So uniqueness in the class that satisfies this
Yes.
estimates.
Yes. And from our reasons, the following consequence follows: that Q satisfies the same inequality with some different, some other constant K. So my time is over. Thank you. See you later. See you next Tuesday.
Sorry? Can I ask a